This lesson is on the vsepr theory, which is a theory that explains the shapes of molecules. Molecular shape is an important property in determining their physical and chemical characteristics. The acronym vsepr stands for valence shell electron pair repulsion, and basically it means that all the electron pairs around a central atom get as far apart as they possibly can. For example, if we had the methane molecule, CH4, we have 1 carbon and 4 hydrogens. They are not going to all pack themselves over on one side of the molecule. Instead, they are going to get all as far apart from each other as they possibly can. And you kind of have to picture that in a three-dimensional shape. The molecule in front, or the atoms in front sticking in front, one's behind, so that all is going to be about 109.5 degrees. For example, if we think of the carbon dioxide molecule, we can quickly draw the dot structure for the carbon dioxide molecule. Carbons have 4 electrons, share 2 with each of the oxygens. Each of the oxygens is going to share 2 electrons with the carbon. Remaining pairs go on the outside as such. That is going to give us a double bond between the carbon and the oxygens. So should I draw this in a linear shape as such? Or another option would be to move this oxygen up here and put the double bond there. The first would be the more correct. Here we have 2 pairs of electrons that are relatively close together. Here they would be 90 degrees apart from each other. That's closer than they need to be. And since these are pairs of electrons, these are pairs of electrons, they want to get as far apart as they possibly can. So the correct shape would not be 90 degrees, but it would be 180 degrees, because now these pairs of electrons are as far apart from each other as they possibly can get, making that a linear triatomic molecule. If we draw the dot structure for ozone, each of these have 6, need 2 electrons. So the central oxygen shares 2 with the left hand, 2 with the right hand. Remaining 2 go as a pair on the top. One of these oxygens is going to share 2 with the central oxygen. Remaining pairs go on the outside as such. Now we've got a double bond on this side, a coordinate covalent bond on this side. So without thinking about vsepr theory, I might put a double bond there and an arrow there. But here we have an unshared pair of electrons on top of the molecule that's going to repel those bonds downward. So you've got 3 domains, 3 regions of electrons around the central atom, and they want to get as far apart as they possibly can. So the correct shape would be, since we have this unshared pair here, it's going to repel the other bonds downward, and that is going to create a bent triatomic molecule. Now those 3 regions of electrons are as far apart from each other as they possibly can get, and that is how the vsepr theory is used to determine shapes of molecules. We'll be looking at 6 different shapes. There's linear geometry, which is 180 degrees apart. Here there are no unshared pairs on the central atom. The only shared pairs are on the sides, so they get as far apart as they can. Bent triatomic can have either 1 shared pair on the central atom as such, or it can have 2 unshared pairs on the central atom, and that's going to cause it to be a bent molecule, and the bond angle ranging somewhere from about 105 to 120 degrees depending on the particular molecule. Trigonoplanar has no unshared pairs of electrons on the central atom, so the shared pairs of electrons all get as far apart from each other as they can, making a bond angle of 120 degrees. A pyramidal molecule will have, in this case, 1 unshared pair of electrons on the central, bending all the other bonds downward, and that's going to give it a bond angle of somewhere around 107 degrees. Again, there'll be variation depending on the particular molecule. And the last 2 shapes we'll be focusing on are tetrahedral. Tetrahedral has 4 shared pairs around the central atom, no unshared pairs, and when they are as far apart from each other as they possibly can, will give that molecule a 109.5 degree. The trigonal bipyramidal molecule has a combination of 90 degrees and 120 degrees between the different arrangement of the atoms surrounding the central atom on that particular molecule. So those are the shapes we're going to be looking at. What I expect you to be able to do with the vsepr theory is if I give you a molecule such as methane, you should be able to draw the dot structure for that molecule. And then look at those molecular geometries and figure out the shape. Here we have 5 total atoms, 1 central atom and 4 peripheral atoms. The only shape that corresponds to that is the tetrahedral. This is the one with 5 atoms. We have the central atom and the 4 peripheral atoms. And so that is going to make this molecule a tetrahedral molecule. So I want you to be able to draw it in the correct shape. And so here's the hydrogen, the carbon, and then again try to arrange this into a 3-dimensional shape, indicating the correct shape of the molecule. And again, that is a tetrahedral molecule, ball and stick structure looking something like that. Nitrogen tribromide. Here we have a nitrogen and 3 bromides. Note there are 4 atoms in this molecule, and the only geometries that have 4 atoms are the trigonal planar and the pyramidal. So this molecule must be either the trigonal planar or the pyramidal molecule. To figure it out, we have to draw the dot structure. So nitrogen is going to share 1 electron with each of the bromines, remaining 2 goes a pair on top. Each bromine is going to share 1 with the nitrogen to give it its octet. Remaining electrons will go on the outside. And now, because of this unshared pair of electrons, that is going to repel the bonds downward, and that is going to make this a pyramidal molecule, with the bromines being bent or pushed downward because of that unshared pair. And so the geometry would look something like this in terms of its shape, being a pyramidal molecule. Sulfur trioxide, here we have 4 atoms, the sulfur and the 3 oxygens. Again, that gives us the possibility of either the trigonal planar or the pyramidal molecule. So let's draw it. Sulfur has 6 electrons, share 2 with that oxygen, 2 with that oxygen, 2 with that oxygen. One of the oxygens share 2 with the sulfur. Its remaining 4 go on the outside. The other oxygens do not share any with the central sulfur. And so now we've got 3 domains around the central atom. We have a double bond and 2 coordinate covalent bonds. So with 3 domains around the central atom, those 3 domains are want to get as far apart as they possibly can. And that is going to make it a trigonal planar molecule. And so the sulfur's here, coordinate covalent bond there, coordinate covalent bond there, and double bond here. Again, about 120 degrees apart for that molecule. And if we wanted to draw the ball and stick structure, would look something like this. Another example would be oxygen difluoride. And put the oxygen in the middle, 2 fluorines on either side. Each of the fluorines need 1. Remaining pairs of electrons for oxygen go on top for its 6. The oxygen needs 2, so each fluorine will share 1 with the oxygen. And now we've got 4 domains around the central atom: unshared pair, unshared pair, shared pair, shared pair. This basically falls into the tetrahedral family. And we have only 2 atoms. And so imagine the central atom with 4 domains around it. 2 of these are going to be unshared pairs. 2 are going to be shared pairs. So we're going to put the fluorine there, and really the correct way to draw it for the unshared pairs would have 2 unshared pairs bending it downward, and that would be someplace around 105 degrees. And so the formula would look, or the ball and stick shape would look something like this. And that would be a bent triatomic molecule. Last thing, how do those unshared pairs affect the bond angles? Why do I say sometimes 105, 120, 109.5? It's because shared pairs repel less than unshared pairs. So let's imagine these 3 molecules: methane, CH4, ammonia, NH3, and water, H2O. Every one of these has 4 domains around the central atom. The methane has 4 shared pairs represented by these lines. Ammonia has only 3 pairs represented by these lines. Oxygen has 2 shared pairs, but nitrogen has an unshared pair there. Oxygen has 2 unshared pairs. So let's think about this shared pair versus this unshared pair versus these 2 unshared pairs. This is a pair of electrons. This hydrogen represents an atom with a nucleus. That nucleus is going to pull up on those shared pairs of electrons, and that's going to reduce repulsion on these other bonds, and that makes that bond angle 109.5. If we take away this atom and don't have a nucleus up there, we get something like this unshared pair. Now there's no atom up here pulling away on those electrons, so those electrons are going to repel those other electrons more, making them bend downward, and that makes that bond angle 107. So unshared pairs repel more than shared pairs, and 2 unshared pairs are going to repel more than 1 unshared pair, making that bond angle 105 degrees. So bottom line there is unshared pairs always repel more than shared pairs, and if the bond angle is less than 120, it's going to push those bonds, changing the shape of the molecule.